Quantum mechanics and general relativity are the two main pillars that form the basis for modern physics. Quantum physics describes the interaction of the very, very small on subatomic scales. It includes all fundamental forces except gravity. General relativity, on the other hand, describes effects on a large scale. We're talking about planets or stars and the effect they have on the curvature of space-time, describing gravity. But what happens when we have to deal with an object that occurs in both small and big scales? A theory that unites these two theories, a so-called theory of everything, has long been one of the greatest challenges in theoretical physics because so far these theories are incompatible with one another. Black holes are objects that exhibit both quantum and relativistic properties. In 1974, the theoretical physicist and astrophysicist Stephen Hawking made a revolutionary discovery that black holes are not entirely black, but instead emit black body radiation called Hawking radiation, coming from the fact that the vacuum of space is not truly empty but full of quantum fluctuations. Near the event horizon of a black hole, particle-antiparticle pairs can form spontaneously. Occasionally, one particle of this pair will fall into the black hole while the other escapes, appearing as if the black hole were emitting particles. This process leads to the black hole eventually losing mass very slowly. The temperature of the emitted radiation, Hawking radiation, is inversely proportional to the mass of the black hole. To be more precise, the temperature of the radiation emitted by a black hole is equal to the reduced Planck constant multiplied by the cube of the speed of light, divided by 8 times pi times the gravitational constant times the mass of the black hole times Boltzmann's constant. This means that smaller black holes emit more radiation than larger ones. Still, this phenomenon is purely theoretical, as measuring Hawking radiation directly is virtually impossible due to its incredibly low temperature, which would be very easily overwhelmed by cosmic noise. Also, the entropy of a black hole, being first proposed by Wittgenstein and then confirmed by Hawking, is proportional to the area of its event horizon and follows the following formula. The entropy of a black hole equals the Boltzmann constant multiplied by the cube of the speed of light times the area of the event horizon, divided by 4 times the gravitational constant times the reduced Planck constant. As the black hole emits Hawking radiation, it loses mass at a rate dictated by the power of that radiation, which for a non-rotating, uncharged Schwarzschild black hole is given by power equals h bar times c to the 6th power divided by 15,360 times pi times g squared times m squared. Because the power scales inversely with the square of the mass loss accelerates as the hole gets lighter, leading to a runaway explosion in its final moments. Integrating this mass loss rate gives the total evaporation time. Evaporation time is approximately 5,120 times pi times g squared divided by 8 bar times c to the 4th power, all multiplied by m cubed. Thus a solar mass black hole mass about 2 times 10 to the 30th kilograms would take on the order of 10 to the 67 years to vanish completely, far longer than the current age of the universe. Hawking's result also started one of the most popular puzzles in theoretical physics called the black hole information paradox. In quantum mechanics, information about a closed system's initial state must be preserved in its final state unitarity. But if a black hole evaporates into thermal radiation, it seems to destroy all information about what fell in. Does information really get destroyed behind the horizon, or maybe it somehow is encoded in some way? Multiple approaches like string theory's holographic duality, loop quantum gravity proposals, and even ideas of black hole type of firewalls have been suggested, but there is really no accepted solution yet. Because black holes connect quantum field theory and curved space-time, they serve as a testing ground for any candidate of a so-called theory of quantum gravity. For example, in the anti-de Sitter space/conformal field theory correspondence of string theory, a black hole in the bulk anti-de Sitter space is dual to a thermal state in a lower dimensional quantum field theory without gravity, offering a concrete realization of how information might be preserved. Similarly, loop quantum gravity calculations suggest that near the singularity, discrete quantum geometric effects could replace the classical Schwarzschild interior, potentially resolving the singularity and altering the end stages of evaporation. Although astrophysical detection of genuine Hawking radiation is practically impossible, analog gravity experiments have begun to take up interest. In ultra-cold atomic Bose-Einstein condensates, engineered sonic horizons mimic black hole event horizons for phonons, and researchers have observed spontaneous emission consistent with a thermal spectrum. Optical waveguides and nonlinear fiber setups have similarly displayed horizon-induced photon pair production, offering us a very small glimpse of hope that maybe someday we might one day test aspects of Hawking's prediction directly in the lab.